I'll just clarify this anyway. Let's start. Sorry, we're a bit late today, but so today we'll continue things that we started out last time. Okay, so we started off with optimization, and we'll look at one of the simplest cases, which is called linear optimization. And I'm guessing some of you have seen this, but we'll just do it from scratch because we want everybody to be on the same page. Okay, so all right. So first, a couple of announcements, and so as you all know, homework 4 is due this Monday. Okay. So there were one or two common confusions that people had. I thought I would just mention those. One is people were not quite sure what the inner product of AX equals inner product of BX. What I meant in particular by something like this, I just meant that you compute the dot products normally, like you do for real vectors, and you take them modulo 2. Okay, that's all I meant. So, and some had questions about whether one side was mod 2 or the other side. So it's just the whole expression. And the other thing which was just asked, what is the question again?
You have to compare.
Correct, the comparisons. Yeah, so for the quicksort question, there's a confusion about how to, what it means by the, what I meant by the running time. So technically I mean the number of comparisons that the sorting algorithm does. But for n large enough, this will be proportional to the amount of work you do. Okay, so you can just even time it. Okay, so that problem is meant just as a coding exercise. Okay, so you just run it for large n, and n should be large enough that you actually see some difference. When it's too small, it'll just be the noise. Okay, and then just report this. All right. And about the project meetings, I think I'm almost over 90% done. There are maybe one or two people whom I'll meet next week. Okay, so, all right. So, okay. So what did we start seeing last time? We started looking at optimization, and we saw that many people had different views about optimization. But we said that it's a very, in a very general sense, you can phrase it as the following problem: you have some variables that you want to optimize, and they take values in some domain D, and you want to find the maximum value of some function f of these variables, subject to a bunch of constraints that involve these. And this, as you can imagine, you can phrase many natural problems as optimization. So we saw the examples of things like scheduling, matching, shortest paths, and so on. And one question that we asked was, okay, why do we care? We know how to solve some of these problems by other means, right? Why do we care? Well, the point is, maybe there are other problems that we could express as optimization. Okay? So that's one answer, but we don't know how to solve by other means. Okay? And the other thing is that there are several techniques that people have thought about for optimization. And the hope is that we can leverage this for your problem of choice. Okay, so those are the two things we said. And let me just recall the matching example. Okay, so this is just the slide from last time. So the matching problem, you have two sets, S and T, and you want to find an assignment of every vertex I to some sigma of I in T. Okay, and sigma should be a permutation. Okay, so this is just exactly the slide from last class. Okay. And we said that you can formulate it as an optimization problem where your variables correspond to whether I was matched to J or not. So xij is supposed to be a Boolean variable, takes 0, 1 values. Okay. And xij is 1 if you are assigning I to J and is 0 otherwise. And then we said that if you have this kind of variables, then you would write the obvious constraints, like every vertex is matched to precisely, every I is matched to precisely 1j, and every j is matched to precisely 1i. So those are these two constraints, and the objective was a little bit, you have to think a little bit to write down the objective. It was the sum of the weights of the assigned edges. Right? So if I was assigned to sigma of I, you must add up things like wi sigma of I. And somebody observed that you could write this as sum over all edges of xij, wij. The rationale here was that if I was, if you look at some j for which j was not sigma of I, that xij variable would be 0. So it would not contribute anything. Okay, so this is exactly the objective that you would like to optimize. Alright, so this is matching. Okay, we will come back to this formulation either late this class or early next class. Okay, so that's why I just put this up. Alright, so the other example we saw, which is a bit more non-trivial, was shortest paths. So here we have a graph, and we said it's an undirected but weighted, of course, graph. And so the variables we said correspond to edges. And so you have some vertex. Let's say I want to find a path from source, which is A, to sink, which is H. So from S to T. And so the solution I would like to have is something that just selects all the edges corresponding to the shortest path. So in this case, I'm not sure what the shortest path is. Presumably it's something like this. So I would like to have a solution that sets xe equals 1 for these things, for the blue edges that I have drawn, and xe equals 0 for the others. Okay. And so somehow I want to enforce constraints that say that among the xe's that were set to 1, okay, there is actually a path from S to T. So this is what we saw last time, and there were 3 different suggestions for this. One was a very interesting one, which was based on the matrix power. Okay, so this resulted in polynomial constraints, which are often hard to optimize, but it's still a very valid formulation. Okay, so it's based on polynomial constraints. Yeah, and then so I presented this cut-based thing where I was saying that if you want a path from S to T, then if you look at any set of vertices that includes S but does not include T, our xe's must be 1 for at least one of the edges in the cut. Okay? And this resulted in a bunch of linear constraints. But we had exponentially many of them. Exponentially many. So it's nice in that the constraints are all kind of clean, but there were exponentially many constraints. So that was the problem with that formulation. And then what if you suggested this, what I in hindsight was calling the flow kind of a thing, where you have some kind of an in degree equals out degree kind of a constraint to enforce that there is a path from S to T. Okay. So this had 2 ideas in it. The first was introducing directed edges and having in degree equals out degree equals 1. Okay. So the observation here was that any path from S to T, you can think of directing the edges as going from S to T. Okay. And you want in degree equals out degree equals 1 for any vertex it's not S or T. For S and T for S you want out degree equals 1, for T you want in degree. And this exactly defines a path. Okay. So this was the other formulation somebody had come up with. Right, so this turns out to be, so this is one example of a non-trivial optimization formulation. And the big picture in all of these optimization formulations was, in some sense, you want to find what the variables are, what the constraints are, and what the objective is. And somehow you should have the property that if someone were to just look at the optimization problem you came up with, and this person had no idea of what the original problem you were trying to solve was. So the solution to this optimization problem must end up giving you a solution to this original. Okay. And this was the thing, this was the main property. Alright, so any thoughts, questions on this so far? Alright, so alright, so I thought I would mention one other example. Perhaps I will mention this kind of in passing. I mean, we'll go over it somewhat quickly. But this is one example that it's quite interesting, and it's another example of a non-trivial formulation. Okay, so I thought I would show you one other example. Okay, which is, and this is the Minus-Time tree problem. Okay, so this, again, we saw an algorithm for it which is quite fast. So what is the problem? You have a undirected graph. We have an undirected graph G, and you have a bunch of vertices, and edges have weights. And your goal is to select as few edges as possible, or in terms of weight. Right? Select a subset of edges of minimum total weight so that the graph is connected. Okay, so you want to find, so we call this a communication backbone in the example we saw last time, a few weeks ago. So the graph has a bunch of vertices. And every edge has some weight. Right, so if you remember in your homework, you saw like a couple of variations of the standard algorithm for this. All right, so this is just to recap the problem. Right, so now how would you phrase it as an optimization problem? So remember, you've got to ask yourself, what are the variables, what are the constraints, and what's the objective that you want to optimize?
Then continuing in the same theme, can we do some x of b, which represents whether or not an edge is in our solution?
Okay. Yeah, so one of the hints should be like the problem definition itself, right? The goal is to select the subset of the edge. Okay, so you could ask, okay, so I will have a variable xe that's supposed to be 0 or 1. And it's, so this belongs to 1. And xe equals 1. So, nicely, so it is 0 if e is not 0. And 1 if e is 0. Alright, so these are obviously other variables. Okay. If you have these as variables, the objective is easy to write, right? So what would be the objective?
Minimize the sum of xe.
Yeah, so then your objective is very easy. So objective is just minimize sum of e of xe times we. So that's very simple. Now, what are the constraints? So remember that, yeah. So you somehow want to enforce the graph is connected. Okay. So how would you enforce the fact that the graph is correct? And the way you should think about such a question is, suppose somebody gave you a bunch of XE, right? So suppose somebody gave you a bunch of XE values. Let's say 0, 1, 1, 0, 1, right? So this is like a smaller graph, but let's say you had something like this. How would you infer, or what constraint could you write to rule out some bad solution of this kind?
Something like to find the number of vertices which are connected using those edges. And if we can find out the number of vertices with the number of edges we have got.
Yeah, so the idea is, okay, so maybe we should try to look at all the XEs that are 1. This will be some subgraph to vision graph. Try to count the size of a connected component in this, and that should be equal to n. So this is intuitively correct, but how would you write this as a set of constraints? So a hint could be, remember that connecting was similar to the problem we had in shortest paths. Connect S to T. Now it's not about S and T anymore, it's about the whole graph being connected. Okay, so can you take a page from that and say? Yeah.
This should be exactly one time.
Yeah, so one idea is, I know how to enforce a path between S and T. Okay? And we saw 3 different ways of doing this. Right? And so what you could say, okay, use my path constraints, but use them for like every S and every T. Okay? So this is an idea that turns out to work. Okay? And actually you will implement this in your homework. Okay? So this is one of the ways in which you can come up with a polynomial size formulation for spanning rings. Okay? So yeah, so it is take any way, take any method we saw for enforcing a path between S and T, and use such constraints for all S. So you say that between every S and every T there must be a path. And this is a perfectly valid way of doing this.
There's a different way of saying that same thing is you could just count the number of edges and it has to be equal to something with the vertices minus 1.
That is correct. But what if, so what he's suggesting is you just count the number of edges, which is sum over EXE, and you say that this is at least n minus 1. So this looks reasonable, right? But the point is, it doesn't enforce connectivity. Like you could have ones like this, and you could have a 1 over here. Okay, like you said, right? You could have a cycle, right? So in this case, you have 5 vertices, and you've picked 4 edges. So if you could additionally enforce that there were no cycles, this would be great. Okay, so in fact, it turns out you can do that. Okay, so you can look at any set of certain size, enforce that there are at most S minus 1 edges between that set, and this turns out to be a valid formulation. Okay, so So idea number 2 is have this constraint along with no cycles. Okay. And this, there is no very short way of writing this. The only way at least I know is for all S, sum over E with both endpoints in S of xe is smaller than equal to size of S minus 1. Okay. If there's a cycle, it has to be S. The cycle between S points, then it should have at least. So this is so this is another totally valid way of doing this. And there's also, you can also write down the same cut formulation that we discussed last time. You can say for any set, there must exist at least one edge that goes between S and its complement. For any set that's not that times. Okay, so that's a third way you can write down. Okay, so that's called the cut formulation. It is for all S, sum over E in the cut S bar of X of E bigger than equal to 1. So for all S that's not equal to either the empty set or the full set. The empty set or the full set, then there will be no empty set. Alright, so why am I doing this? So I wanted to emphasize that in some sense there are many optimization problems you can come up with for a particular formulation. Okay? For a particular problem. Okay? And some may be better than the others. For some you will be able to optimize. And like in this case, these constraints look exponential size. But it turns out sometimes you can still optimize over exponentially sized sets of constraints. And so in some sense it's good to keep in mind that you can write different formulations for problems. Okay. So that's the reason I want to illustrate with a bunch of examples. Alright, so again, so quickly zooming out, right? So we saw a bunch of examples of
Can you go back to the previous slide?
yeah.
So when you were talking about the idea too, can't it be possible that we are selecting some edges that do, like there's some counts to n-1, but still we are not making sure that all the vertices have been used. So like how are we ensuring that thing is?
Right. So this takes a little bit of a proof to show that this is equivalent, right? So then the question becomes, so I guess the question you're asking is, suppose you have n-1 edges, and for any set of vertices you have this constraint. Could it be that the graph is not connected? Right? That's what you're asking. Okay, and
No,
yeah.
And then the graph could be connected, but we are not taking, like we are not reaching a particular vertex. I mean, we are not considering one of the edges that leads to that vertex, and we are considering some other edges.
Right, when I meant the graph, I meant the graph of all, graph just restricted to edges for which xe equals 1. Okay, only the edges that you've picked. Okay, so what you're asking is, could a situation like this happen in some sense, right? Like you picked n-1 things, but somehow you could not reach one portion of the graph. Okay, so the claim is that this cannot happen. So you can argue that if such a thing were to happen, then there has to be a cycle in the graph. Okay, and that is ruled out by constraints of this kind. Okay, and we can think a little bit about what might be the easiest way to prove that fact. Okay, so if you have at least n minus 1 edges. Okay, so or let's say you had exactly n minus 1 edges, then someone needs to run device. Alright, so yeah, so you can actually prove this by saying that if you have exactly n minus 1 edges, then there has to be one vertex with degree 1, and you can try to remove it, and you can prove this kind of things by induction. Okay, so we can talk about this. Okay? But what she's asking is a valid question, right? So for every formulation, you should be asking this fact, like, is my formulation accurately capturing the like the actual constraints that I want to satisfy. Like in this case, I want to find. Yeah.
This might be a silly question, but could we use some kind of meta optimization to figure out what formulation is the most optimal?
Yeah. So how do you do
Such as
So there's, there are heuristics of this kind, right? Like so there are things that say, okay, you start with few constraints, you see what is not. You see that somehow the solution you obtain is not satisfactory, try to add more constraints. Okay, so there are methods of this kind. Okay? But to the best of my knowledge, we usually proceed by giving a list of constraints and saying that these exactly capture the problem. Okay? Yeah. But heuristically, you might, so you might start with a smaller set of constraints and hope for the best, hope that everything else will be satisfying. Alright, so just a quick summary. So if you want to write a problem as optimization, you got to figure out these basic questions. Okay, and you want to also reason about, do these constraints to argue about constraints capturing the problem. And these exactly mean the questions of the kind that she asked. Okay, and sometimes it could be non-trivial. We'll see more examples of this. Alright, so far we've seen how to express problems with optimization with the hope that we can answer this question, right? Like that the actual optimization problem can be solved efficiently. So that's the hope for actually trying to write a problem as optimization. But it turns out we should start with some bad news up front. Okay, so the bad news is that all the formulations we wrote down so far are actually intractable. Okay, so it sounds like very bad news, but so can you guys guess as to why this might be? Why I say that these are actually intractable? Yeah.
Because the exponential number of constraints.
Well, sure, but for some cases we had polynomially many, right? Like for matching, you had polynomially many. For even for shortest path, we saw that this directed approach, probably used this last time, was had polynomial size, right? So let's say it still has polynomial size. I still want to say that this, at least the way we wrote it down, it was in fact. Yeah, so the way we wrote down the formulations was by saying that these xi's were supposed to belong to either 0, 1 or belong to some domain, okay, some discrete domain D. Okay. And it turns out that if you want to do optimization under such restrictions, we have no general methods for doing this. Okay, and so discrete, or this is called integer optimization. So discrete optimization is generally quite hard. Okay, so we will formalize this later in the course when we talk about interactivity and so on. Okay, but roughly speaking, yeah, optimization over such discrete domains is quite clear.
So maybe this is a dumb question, but since we're running all these algorithms and programs on the computer, which is fundamentally discrete, because you've got like memories, then isn't all optimization running on a computer intractable by that question?
Well, so what you're talking about is more of like an algorithm running on a computer. So here we are talking about the optimization formulation itself being discrete. Okay. So ordinarily, what happens is that you have some optimization. Let's say you're running some continuous thing like gradient descent on a machine with finite precision. Then sometimes you're simulating an infinite precision thing using finite precision. So all our guarantees would be about the infinite precision thing, and we hope that the finite precision part accurately simulates it or doesn't deviate too much from that. Okay? But the formulation itself was continuous. Okay? Yeah, so that's a very good question. So it's so here the formulation was discrete. Okay, so that's the reason it's discrete. Alright, so this is some bad news, but there's also some good news. Okay, so under some fairly reasonable assumptions, so continuous optimization turns out to have efficient algorithms. Okay, so for a class of problems. So one very interesting class that we'll see is when you have linear constraints and a linear objective. Okay, so these are called linear programs. And these turn out to be a special class of what is called convex optimization, which we have seen earlier in this class, if you guys remember, in the context of local search. Okay, so so these turn out to be special cases of a more general thing called convex optimization, which is in context of local search. All right. So there's some classes of continuous optimization that we can actually solve efficiently. So here also there are many classes that we don't know how to solve. And in particular, this is the reason I was very reluctant when somebody was mentioning, when you were mentioning polynomial constraints, right? So if you have variables that have polynomial constraints, it turns out that even continuous optimization is quite difficult. Okay? So usually you want constraints that are linear or somewhat linear. Yeah, so things that are related to convex and function. So yeah, so that's some rough sketch of what is possible. Okay. So now the main challenge becomes, okay, so can you express the problems that we have of interest, okay, which are often discrete optimization problems, as some of these continuous optimization things? And if so, let's say you solve some continuous optimization problem, you get a solution. How do you get back an integer solution from? So those are the kind of problems we want to discuss. So that's the general goal. Okay, that's the goal of the next few lectures. And today we'll start off by looking at some of the simple cases. Okay, so today we'll talk a little bit more about linear and convex optimization. Yeah.
Are those two different things? So
Which one?
linear and convex.
Yeah, so as I was saying, right? So linear optimization is a special case of convex optimization. So it's but it turns out for linear you can often get better algorithms.
But then convex optimization is just anything over continuous.
Yeah, so it's we'll formally recall the definition. So it says you have a convex domain, you want to minimize the convex domain. So that's yeah. So linear functions are also convex. So that's why they're a special case. All right. So we'll talk a little bit about these things. In particular, we'll talk about the geometry of linear optimization. Okay, so it turns out linear optimization has some very clean geometric properties, and many of the algorithms actually come from understanding the geometry. So we will see that, and next we will also start, if we have time, maybe it won't happen. We'll start looking at how to express continuous problems like matchings or some things we saw as linear optimization, and try to see, okay, so suppose I solve it not over the discrete space but over continuous space. Are the solutions still useful? Okay. So that's what we want to see about this. Alright. So let's start with some quick introduction to linear programming. Okay, so actually just as a show of hands, so how many of you have seen some form of linear programming before? So a decent challenge. Alright, so we will, so I'll be somewhat, this might be a little repetitive for you guys, but let's just do this anyway. Okay, so it's very simple. So what is linear programming? Okay, so you want to maximize and minimize. So let me just write. So I'll have to take a couple of minutes break to charge this. Right, but before that, any questions for yeah?
Why do we call this linear program?
Yeah, so why call it a program as opposed to optimization, right? Why not just call it linear optimization? So that's a good question. I once Googled for this and I used to know the answer, but it's a boring answer. I don't remember what it was. So it doesn't have quite the interesting story as dynamic programming does. Yeah. Dynamic programming came out because of some funding reasons. So, yeah, but this is not quite that. Hopefully this will yeah. Alright, so what is linear programming? So you have a linear function. Let me start with variables. Right? So variables, I will call them x1, x2 to xn. These are now real value variables. Okay. Each xi is a real number. And you have the objective is also a linear function. Is some c1 x1 plus c2 x2 cn xn, which I will just write it as c transpose x for now. Okay, so x will denote the set of variables, and c will be the vector of c1, c2, c. So I'll just write it like this. Right. So the constraints. And you either have a maximization or a minimization. So note that they are equivalent for linear functions. Right? So maximizing c transpose x is the same as minimizing minus c transpose x. Okay, so this is the same thing. So we'll stick to minimizing. And the constraints are you have m linear constraints. So n is the number of variables, m will be the number of constraints. So this also I will write it as, I will write one of the constraints explicitly. So you have a11 x1, a1 xn is let's say less than equal to b1. Again, this choice of less than or equal to is arbitrary. I reverse the signs and everything become bigger than. And so this one I will write it as a1 transpose x less than equal to b1. So a1 is a vector of a11, a12. And you have other constraints like a2 transpose x less than equal to b2. And am transpose x less than equal to b. Okay. So this is the very general form of linear programming. Alright, so how do we think about linear programming? Right? So the main idea that I want to emphasize is that you can always think of these constraints as defining a small portion of n-dimensional real space. Okay, and this viewpoint is very useful for all algorithms. Okay, so let's just illustrate using 2 dimensions. Okay, so let's take a very basic linear program. So you have variables x1 and x2 along the real numbers, and you have x1 plus x. You want to minimize, let's say, x1 plus x2 subject to the constraints. Okay, so this means st means subject to constraints. Subject to, let's say, x1 plus 4x2 is bigger than or equal to 10, and x1 plus 5. Okay, so something of this kind, right? So now you could ask yourself, okay, so how would you solve a problem like this? Okay, so that's the thing that you want to understand. And so the algorithm I'm going to demonstrate to you is, the first one is just simple geometric way of looking at things. Alright, so the first thing you ask yourself is, what do these constraints mean? Right? So I want x1 and x2 to be real numbers. So you can try to plot out the set of real numbers. So this is any x1 and x2 can be viewed as a point in the plane. So you have the x1 axis and x2 axis. And now this is very easy, right? So x1 plus 4x2 bigger than or equal to 10 is something that maybe looks like this. Yeah, I apologize if today we will see a lot of bad figures. Yeah, alright. So you have something like this. And x1 less than or equal to 5. Okay, so this will be something of this kind. Okay, you want x1 less than or equal to 5. Okay, so this everything on the left of this line would have x1 less than or equal to 5. Okay, this is 5. Right? So what is the set of points in the plane that satisfies both of these inequalities? So it's that top, corner, right? So it's this thing, this region. So this is the region in which our optimization problem is working. Okay. So that's how you think of linear optimization. Okay, so it defines a region of space, which in this case is defined by just lines in 2 dimensions. So one general observation. So each constraint is what we call a half space. Okay. So the set of all feasible solutions to just one of the constraints, it's the picture I drew, right? So it's defined by, let's say the first one, it's defined by everything to the right of that line that way. In general, in n dimensions, it will be a plane which defines the equation, and everything on one side of the plane will satisfy the inequality, everything on the other side will not. Okay? So this is what's called a half space. Okay? So each constraint is a half space, and the overall set of feasible solutions is an intersection of half spaces. Because you want all the constraints to be satisfied. And each constraint, one constraint being satisfied means that that point x belongs to that half space. And if all the constraints are satisfied, then it belongs to all the corresponding half spaces. And which means that it belongs to the intersection of all these half spaces. So that's why we call this an intersection of half spaces. Alright. And okay, so now getting back to this example. Yeah.
So this is defining the domain where we are minimizing that function.
That is, yeah. So this is a little different from the way I used the word domain before, right? So I was saying x's belong to some domain. So there the domain was like 0 or 1, something like that. Okay? But now it's each xi is an arbitrary real number. So you think of the domain of each variable as just a real number, as a set of all real numbers. But but if you look at the whole vector of x1, x2 up to xn, it is restricted to lie in this intersection of half spaces. The constraints restricted. So it's a matter of definition, but yeah. Yeah. Alright. So any other? Yeah.
We do have the domain comprehension.
Yeah, so are you saying that, like in this case, this is an infinite, the set of all feasible x's is an infinite set? Is that what you're talking about? Yeah. Yeah, so we don't technically require this. Okay. So what he's asking, actually this example probably will illustrate this. So what he's asking is, every point in this cone that I drew up here is a feasible point, and this cone is infinite. So this often happens in linear programming. Okay, so your set of feasible solutions could be infinite. And sometimes for this reason, your objective value could be minus infinity. Okay, like if you're trying to minimize, maybe your objective value could be minus. Okay. So in which case that's fine. Okay, so it is what it is. So yeah.
The infinite point is not in the intersection of the half space.
I don't know about some projective geometry like definitions. So we define everything in that cone as being the intersection of the half space. Okay, so yeah, let's leave it a little bit informal. Let's not try to get too formal about the infinite points. Okay, alright. So that's that. Okay, so here you have this thing. And now, okay, so in this example, how would you try to minimize x1 plus x2 in that cone? What would be a good way of minimizing x1 plus x2 subject to being in that cone?
Select the largest negative x1 value and then select the corresponding x2 value that's still in the center zone.
Well, in this case, the largest x1 is probably minus infinity, right?
Yes, that's a problem. But
Okay.
you do minus infinity plus 1, and that's really this. But a very, very large
Okay.
x value will be our optimal solution.
So, sure, I mean, what you're going to say is that in general, but would this kind of an approach work in general?
If I program something that was looking at a graph,
Okay. So yeah, I mean, so what he's suggesting is, if you want to find a point in this feasible set that has minimum value x1 plus x2, you could try, first looking at the smallest x1, and then the smallest x2, and so on. It's subject to that. But it turns out this doesn't always work. I mean, because once you've committed yourself to the smallest x1, it's like doing some kind of a greedy optimization. Okay? So maybe the x2 you get is not as good as the x2 you might have got with a different x1. Okay? So yeah, I mean, I can give an example of this if you really want, but yeah, so you can come up with an example of this kind, maybe where it's like this, and you have your feasible. Let's say this is your axis, and maybe you have an object like this, that is the intersection of all the half spaces. Let's say this is your feasible set. Now, if you want to minimize x1 plus x2, this point is worse than this point. Okay, but this is the point that has the minimum x1. It turns out that for this point, the x1 may be large, but the y is correspondingly much. The x2 is much lower. Okay. So these kind of greedy methods don't usually work. Okay. But you can think a bit more systematically, right? So what is yeah, maybe you were trying to say.
Well, so the problem is you have the vertices off it, nice, and we can look at every intersection of our constraints. And try those.
We will come to that. All right. Yeah. Yeah. So you could ask yourself, okay, so maybe this is the point that has the least value of x1 plus x2, right? But intuitively, yeah. So how would you argue?
Why that's
Yeah. Why is that?
because I'm solving these two inequalities.
Oh, right. So you're saying that, but it could be that the minimum is minus infinity.
Well, if you let x1 go into minus infinity, the first constraint says that x2 would have to go positive.
Right. And in this case, it so happens that it has to be a little bit higher or something like this. Okay. So we'll have to verify this. It's not very obvious from this constraint. I mean, from my figure at least, that this won't happen. So the answer you said is correct. Okay, so let's see how you do this in a more systematic way. Okay, so what you do is, so what does it mean that you want to minimize x1 plus x2, right? So geometrically, what it means is that, so let's actually try a different approach. Okay, so let's try to see what is x1 plus x2 equals 0. What do these curves look like? Right? Like x1 plus x2 equals 1. So these are called level sets, right? So these are, we think of them as like contour diagrams, something like this. And how do these things look like? Right? So in the 2D plane, these are very easy. Right? So these are x1 plus x2 equals 0 looks like this, this one looks like this, this one looks like this, and so on. And this is set of all points on which x1 plus x2 equals 2. And this one is set of all points on which x1 plus x2 equals 1. So intuitively, if you want to find a point that has the largest value of x1 plus x2, you've got to be looking somehow in this direction, which is orthogonal to all of these points. And you must be looking for the furthest point in your feasible set along this direction. Okay, so if you have your feasible set being something of this kind, maybe this was vertical, right? So this was vertical, and this was your feasible set. Now you look in some sense in this direction, which I will call x1 plus x2, and you look for the furthest point. Okay? And imagine doing some kind of a sweep where we bring a plane of this kind and we move it all until it hits this feasible region. Okay? So geometrically, this is what would happen, and in this example, you'll realize that this is indeed the point. Okay, so let me not. I mean, this is a slightly hand-wavy argument, but let me write down this observation. Okay, so it is. So the objective function defines a direction, so which is in this case C. and the optimum point is the furthest point in the feasible set along this direction. So why this is useful we'll see in a little bit, but this is one simple observation that I want you guys to do. Okay. So and the way you think about this is you think about the level sets, which is think about x1 plus x2 equals 0, x1 plus x2 equals 1. These are all planes that move in a certain direction. Okay. And now the minimum just means that you want to move, that you want to be as, you want to move in some sense from top to down, see how far you get while still intersecting the feasible. Okay. So that's how you define it. So that's the direction, and it's the furthest point in the feasible set along this direction. And in this, and if you think about this a little carefully, you realize that that direction turns out to be minus c. Okay, so remember c was this objective function, right? So we said that c transpose and x was the objective value. You want to minimize that. So minus c is the direction in which you want to be as well. So this is what this is. All right. So why do I have this characterization? So the reason I have this characterization is that now I want to make the following claim. Okay, so I want to make the claim that as long as the feasible set is finite, the optimum is always achieved at one of the corner points. So this, remember my aim is to show you guys how you would solve this kind of a problem. Okay? So I'm trying to prove some structural property that the optimum must satisfy, so that I can go ahead and look for this stuff. Okay? So that I can go exploit this problem. Alright, so our observation from before is that you had a characterization of what the optimal point is. And I now want to claim that suppose the feasible set and I will denote it by set of all x such that A1 transpose x less than to B1, A2 transpose x less than to B2. This is how we define the feasible set, right? So suppose this feasible set is finite. Then for any c, for any c, okay, so c again is an n-dimensional thing. The optimum is a corner point of this video. Note that I haven't actually formally defined a corner point yet. Intuitively, in 2 dimensions, you understand what I mean. Okay, by corner point.
Well, I mean, so it seems like you could also just be an edge, so that's not.
Yeah, so what he's saying is, I mean, in some sense, if I try to optimize it, what if I have my feasible set looks like this, okay? And so this is my feasible set, and maybe it's finite, so maybe it looks like this. Okay? and the direction in which you want to optimize is, let's say, something that goes along this. And it exactly happens to be perpendicular to this edge of this polygonal region. Okay? So yeah, so in this case, what happens? Yeah, so in this case, this entire segment is a solution, and this is a degenerate case, in which case you can also say that this point is a corner point, and it's also a middle. Okay. So yeah, so I thought I could sweep this under the rug, but it's a good little point. Okay, so the formal statement would be there exists an optimal point that is also a corner point. Okay, so in this case, in some sense, the phrase the optimal point is not well defined. Okay? There's no the optimal point, there's a bunch of optimal points. Okay? And what you will be able to show is that there is a corner point that is also an optimal. Maybe I'll say an optimal point is a corner. Okay? So there is some.
Well, comment. Is that with the contact finite particles? It is still using the same study.
Okay, so right. So what he's saying is that the feasible set, because I've defined it as a set of real numbers, is finite. I should not be calling it finite, I should be calling it bounded. Okay, so yeah, this is again a good point. Okay, so I should be good catch. Okay, so this is bounded. Then for any C, there exists an optimal point that's also a corner point of yeah.
But the number of constraints there in the physical set, that was fine.
No, so that was finite even in the unbounded case, right? So I mean, like in this example that you saw, where the solution was a cone, where the solution was this cone, which was an infinite cone, it was just defined by two constraints. Okay? So yeah, what I mean here is that it's actually bounded. This is very good. Yeah. All right. So this is the theorem, and so the proof of this, I won't do the formal proof of this in general, but the proof of this, if you think about it, follows exactly the kind of reasoning that his question raised. Okay? So I have argued that the optimal solution is defined by the furthest point along a certain direction. Right? So we said that the optimal solution is defined by the furthest point along a certain direction, and this direction was minus C. Assuming your problem was minimization. Then, so you have some feasible set, and you want the furthest point in this feasible set along this direction. So now what you can do, so I will give a hand-wavy proof of this, a literally hand-wavy proof. So this is one of the topics in which we will actually use intuitive proofs, because when you write down the math, it looks more confusing than it actually is. Okay, so the intuition turns out to be much nicer than the actual the proof itself. Okay, so I'll first do a hand-wavy. Okay, so what is the idea? So we want the furthest point in the set of in this feasible region that is along this direction minus C. Okay? And how do you find such a furthest point? You start at any point and you keep going in that direction until you hit one of the, in some sense, the sides of this figure. Okay, like in a 2D plane, let's say you had a region like this, and your point and your direction was something of this kind. So you would start somewhere, okay, in your region, and you would go like this, and maybe you hit this direction, okay, this maybe in the figure it looks too orthogonal, but let's suppose that this angle was less than 90 degrees. Okay, so if this angle was less than 90 degrees, then I claim that you can now move so that you still go in some sense along this direction C. How can you move if, so how would you move in this case? Yeah, so you would end up moving in this direction because, again, this is a bad figure, so this is, think of a picture where it actually looks like this. Okay? So now you would move along this direction, and now you would end up at a corner point out here. Okay? So this is a very hand-wavy proof, but in high dimensions, what ends up happening is that when you move along a certain direction, you will hit one of the constraints first, and then you keep. Now you stay on this in high dimensions. This kind of a line is called a face. You stay on this face, and you keep going down along one of these directions. And you can always argue that there is some direction which you can actually go. And that turns out to be this. Okay, so again, I'm not going to do this. So there's also a sleek way of doing this, which we might see later. But yeah.
So it's also, we're relying on the shape of the convex, which
Exactly. Yeah. Right. So we are relying on, for example, the absence of something of this kind. Okay. So we are using the fact that. So we're using the fact that if you try to go down along this direction, and maybe you had a feasible set. Okay, maybe that's the wrong direction. But let's say you had a feasible set that looked like this. Okay. And maybe your direction of optimization is something like this. Okay, so this is non-standard. I don't know what I think it's not that. Hopefully my writings will be preserved. Okay, so we will see. Yeah.
So while we're waiting for the question, when it's like a linear objective and your constraints, how should we decide whether we should use linear programming or a graded space method?
Yeah, we will come to that. Okay, so his question is, so if you have a linear optimization problem, should we use some geometric algorithm of this kind, which kind of goes via the planes, or should we use some gradient-based method? Okay, so it turns out, in practice, a lot of the times these geometric simplex type algorithms work very well. Okay, but in theory we don't have very good bounds for them. Okay, so the best known bounds for simplex are exponential. In fact, you can come up with examples where simplex does really badly. Okay? But usually in practice it seems to work very well. Okay? So for this reason, people still use such geometric methods when solving linear programs. Okay? But you could also use convex optimization. You could use what are called interior point methods, okay, which try to go through the interior of the polygon to actually find the optimal thing. And those turn out to work pretty well also. Yeah. Okay, so this moment of truth will not fall out. Okay, good. So, all right. So this is so this is a hand wavy proof. Okay, and what we showed is that An optimal point is a corner point for this field. And the reason, yeah.
What is the difference between what you just described and gradient descent?
Technically speaking, there's not, but yeah, proof is like the proof of gradient descent is similar. Yeah. So noting that like the gradient is basically the direction of C. This is what it is. Yeah.
What about the differentiability of the equation? Of that
Right. So you have to move in this feasible set, right? Yeah. So this is the reason there is a variant of gradient descent where you keep projecting back.
so breaking
No. So there is this thing called projected. Okay, for those of you who maybe have not seen gradient descent, so it's a more general algorithm that I guess we've seen this. It's a local search type algorithm. It always moves along the direction of the negative gradient in order to minimize the function. The problem that he just brought up is that sometimes you could go outside the feasible set. Okay? Like your gradient direction could take you outside the feasible set. But it turns out that there's a very general fix for this, which is you project back to your feasible set. Okay? And projection is defined as the closest point in your feasible set to this point. And if you hit a fixed point, then you have already found the optimum. And so this is just FYI for that. Yeah. But there's a very general fix. All right. So this is something that we have shown, and this now gives a finite time algorithm, right? So we have proved this informally. This is now very real problem. Okay, so let me just explain why this leads to an algorithm, given that we just have a couple of minutes left. Okay, so I want to say that this observation that the optimum point is a corner automatically leads you to a finite time algorithm. Maybe it's not the most efficient algorithm, but it is a finite time algorithm. Can any of you think why? Maybe somebody else? You don't know. No, but I'll get you in a minute. Okay, so yeah. Yeah, so the obvious answer to this would be, I know that my optimum point is a corner. Okay, so try all the corners. Right? And then the question then becomes, okay, so how do you find all the corners?
See where the constraints intersect.
Yeah, so the corners, at least the way I have defined them, at least in 2D this is very obvious, is that you take every pair of constraints and you see where they intersect. Okay, and that should give you a corner. And you, in this manner, you can try basically all possible. So this is somewhat feasible for 2 dimensions because you have m constraints. You try all m choose 2 different ways of choosing corners, and you do it. But the moment you go to high dimension, right? Like if you go to d dimensions, now you've got to choose not just two constraints, but you've got to choose d constraints. And then the problem, as you can see, becomes more and more messy, right? Because you got to choose all possible m choose d tuples of constraints, and each of them could actually be a corner point for you. Okay, and you've got to check all of them. And this turns out to be infeasible. So there's a clean fix for this, and this is called the simplex algorithm, where you don't try to search all corners, but you do some kind of a local search among the set of corners. Okay, so you say that okay, I am at a corner point, I move to a neighboring corner point. And how you do this turns out to be a little bit of an exercise in algebra. We'll see this next time. Okay, So the details are actually not very important, so we will do a hand wavy argument of that also. But the point is that you can do this somewhat better. And yeah, and next time we'll also see why you won't get stuck. That's more interesting.